incredibly rich information here and incredible opportunity, but also danger, because this is incredibly sensitive, the most personal information that you can provide. So we have another project going on in my division that we call Aura, and the underpinning philosophy behind Aura is to build a distributed service that is really your digital self. It is a representation of you, your preferences, the things that you have spoken, the conversations that you've had, the things that you've read, the things that you've purchased, your sensor streams, your blood pressure on a minute-to-minute basis, your family history, significant events. All of that can be your genome. All of that can be stored in your Aura, and it knows everything about you. But the key thing, the most important thing, to get this level of personalization that will drive these continuous services that will make your life better, is that your Aura, or this cloud service, has to operate on your behalf, and the data have to be private. You have to be able to trust that it is not leaking your genetic information to insurance companies or to your enemies. And in this model, all of the information there is encrypted, and all of the devices, your PCs, your phones, your slates, are just caches that contain Aura data and Aura services and operate on your behalf. And then third parties can attach to your Aura through very, very carefully defined interfaces and provide security tokens that gives them permission to access only the restricted subset of information or services that you have granted them permission to access. Okay, so this is an example of the sort of infrastructure that we will need to build to provide true personalized continuous services to a wide number of people. So I would say that the opportunity here, if we do move to this fifth wave that we're calling continuous computing, is to leverage the cloud with very carefully defined security, services on public data that everyone shares, and services on your data, and the ability to merge them without leaking information. Rich clients that have sophisticated sensors, new and augmented types of interaction, and that do processing anticipating what you need, that are working on your behalf, right? And things that move between the two. Things like generating context awareness is partially client and partially cloud. Being aware of your environment is partially client and partially cloud. There are the things that the client senses, and then there are things that the cloud knows about what's happening on the next city block or down the road. And those need to be fused and merged to take that awareness and build this whole set of very rich experiences. So that's what I see as the opportunity to really define a new model of computing where people are continuously interacting with personal services and things are provided for you. Okay, so I view that as good news. That's opportunities that we can all go out and seize and start building systems to deliver. And there's tremendous potential profit, and there's tremendous commercial opportunities for Microsoft, for our competitors, and for our partners. Okay, but there's a challenge. And for those of you that know my history, I'm an old processor guy, and so this is something that keeps me up at night, and it's a little scary actually for those of us working who've been working in the hardware space. And I know that there are many people in this room who are very sophisticated hardware developers and silicon experts, and so forgive me if I'm telling that set of you something that you already know very well. So Gordon Moore, in his classic 1965 paper, observed that the integration of more and more silicon or semiconductor devices onto individual components, onto integrated circuits, was doubling at a fairly consistent rate. And he predicted that that doubling would continue. And that exponential rate in integration of circuits onto silicon became known as Moore's Law. And of course, this exponential growth, and I put it in quotes because exponentials don't go on forever, okay, by their very nature. And there are people, there are thought leaders in our community who have gotten rich selling books talking about these exponentials continuing for 40 years. Okay, I won't name names, but you may know who they are. Okay, and so This is a false claim. When we go back to the Intel 4004 with tens of thousands of transistors and go to today's modern chips with hundreds of millions or billions of transistors, we've ridden this exponential curve in integration and power efficiency and performance for almost 5 decades now. But that exponential scaling will someday come to an end. And so if we think about the very basics of chip performance, how do you really measure performance? Well, it's the frequency of the chip times the instructions per cycle that you can actually exploit. And that can be on one processor core or across many processor cores. And then the power consumption is proportional to capacitance times voltage squared times frequency plus leakage. And of course, there are second-order relationships between all those that we don't need to discuss today. So if you scale down to another generation of semiconductor technology, from 45 nanometers to 32 nanometers, for example, you are able to reduce the supply voltage, and you get significant savings, a cubic reduction in power at a linear loss in performance, but then you can juice the performance back up and still run much more efficiently. Okay, and Dennard's favorite paper in the early 70s from IBM, talked about a methodology for scaling transistors from one generation to the next, where you scaled all of the dimensions of the transistor, length, width, oxide thickness, doping, so that you would keep the electric field across the oxide constant. And so for those of you who don't remember your transistor operation, you have 2 terminals, your source and your drain, and a gate, and you put an electric field on the gate. Here we have an insulator here that pulls up electrons or holes, into this channel and permits current to flow across the channel from the source to the drain. And so the efficiency of that transistor, of switching that transistor, is obviously incredibly important. And as we scale down with Dennard scaling, we've been able to make our transistors faster, smaller, and more energy efficient each time we scale down. In some sense, it's been a dream, right? Each time you scale the technology, things just get better along all of the axes. And so that's how we've driven such enormous improvements in performance and efficiency that allow us to run software in our pockets that 30 years ago was unimaginable to run even in a large machine room. But what's happened now is that the gate oxides, the insulator, has gotten so small because we've scaled so deeply that we're talking about just a small number of atoms preventing, isolating the gate from the channel. And companies have gone to more esoteric materials like hafnium dioxide to stave off, that point at which we can't shrink that any further. So since we started to run into these atomic limits, what's happened is that first the speed of the transistors started to flatline because we're no longer able to stay on the Dennard scaling curve. We're able to scale some dimensions, but not all of them together as they prescribed in that initial paper. And so this chart from some of my colleagues at Microsoft and from researchers at Stanford shows normalized capabilities here on the y-axis and years here on the x-axis. And so these different curves, this shows you, these are all measurements of actual processors. This shows you with a curve fit to each. This shows you the number of transistors on chips, from about 1970 to today. The Dennard scaling paper is here in 1974. And we see clock speed in the dark blue here and power per chip in the blue. And then the performance per clock of individual cores, or ILP, here in the purple. And so what's pretty clear here, is that we've hit a bunch of limits. And the shift from single-core chips to multi-core chips was just the first sort of instance of those limits. We didn't all of a sudden shift to multi-core chips because the industry decided multi-core was the right way to go. We shifted to multi-core chips because performance started to flatline, and we didn't know what else to do with all these transistors that we keep getting. So the number of cores has been growing exponentially, but because of power limitations, the number of cores will soon also stop growing leading us to a point at which the amount of computation we're able to squeeze out of a general purpose chip is flat. And that is a fundamentally different era than what we've been in for the last 40 or 50 years. So that leads us to something that I call the customization conundrum. So if you are in an era where power is limiting how much you can squeeze out of silicon, but you have more transistors than you know what to do with, you have more transistors on your chip than you can actually power, you have both an opportunity and you have a problem. So what people have done is to start to specialize. And of course, there's always been some specialization for narrow markets. But if you look at energy efficiency and compare it with, in some sense, the number of workloads that you can run well, or in this case, the number of processors that you can fit to put on a given chip, a general purpose processor, like an ARM core or a Pentium, is actually incredibly inefficient compared to specialized ASICs. We all know that. But the difference can be orders and orders of magnitude, as many as 3 orders of magnitude. And then in the middle here, you have a range of specialized cores. And then you have sort of dedicated fixed functionality hardware like ASICs. But now we've reached a point where our general purpose processors are not going to be able to get very much better. They'll get a little better. You can tweak the microarchitecture. You can maybe put in some new instructions. But the era of exponential growth for those has ended. And so what everybody is doing in the industry now, or will be in a few years, is trying to figure out how do we provide silicon where you have to make an enormous investment to design it, and it has to run in as many places as possible, but we need to specialize it to start getting the efficiencies we need to make it better. And so in some sense, you can view this through a model, which I just used a triangle, where you have 3 factors you're trying to improve. You're trying to improve efficiency, and you want high volume, and you want low upfront engineering costs. And so what's happened in the industry, in the general purpose industry, by companies like Intel and AMD and others, is that they've produced chips with very low efficiency compared to the number of transistors. Massive amounts of speculation, massive amounts of caches, really general purpose. They run everything well, no matter what the software is, except for corner cases that are perhaps memory bound. But they make up for that by having very high NREs that are amortized over incredibly high volume, because they haven't specialized anything. But now if we need to bring the efficiency up, and we specialize, that may drop our volumes, which means we might have to drop our NREs. But the design of chips is getting more expensive as we increase the degree of integration and reduce the process node and have all the design rules as we're getting down to atomic dimensions. So we have a real challenge here. Right now, in some sense, we've always been able to get 2, but now we need all 3. And so this is really the conundrum. How do you build chips that can be both specialized and highly efficient, but can be very high volume and reach a very large market? And if we don't solve this problem, I think it's going to be very hard for us to provide the sort of capabilities that I was talking about in both the data center and in the clients. Because the data center just needs to get more and more efficient, and the clients need to get more and more capability per unit of battery. So that's our challenge. So I'm going to switch now and talk about and conclude my talk with one other project that we've been working on in my group to try to address this. And so if I think about not so much specialized circuits,